Okay, so let's go back to the slide. The next approach for the performance tuning is like some people call it a black art, because you sometimes in some of the cases you generally need to have a mysterious or secret knowledge how to tune your existing infrastructure, because like it's highly recommended that you cannot going to tune each and everything at a whole go. Just tune one of the parameters, see how much improvement you will see after tuning that parameter. And because that parameter which you are going to tune it might going to improve the performance of your existing infrastructure, or it might make the situation adverse. So just tune one parameter at a time, see how much improvement you have gained after that, and after that let's move to the other component if that component doesn't help you. So like a generalized example, you have a lot of parameter inside your cctl.conf. Just change one parameter at a time depending upon your the problem you are facing at that particular moment of time, and see how much improvement you have gained after changing that parameter. Okay. Like whatever we are discussing it right now, whether we are changing the something on the application side or on the kernel side, the ultimate goal of us is to get the best possible response time or throughput. Okay, we are going to discuss this later. And the last part is like set a clear and realistic expectation with your management. So this is one of the most important aspect which many people ignore. For example, what is considered an acceptable performance for you might consider a bad performance for other users. So let's say you are hitting your internal website which is loading for you in a period of 2 seconds, but for some user it is loading in like for example in a 10 seconds. So for that user this is the acceptable performance, but for you that is not acceptable performance. So when you are going to put your project in your development environment, please set up a baseline that this is the response time you are expecting from your application. And once you set up your baseline, you can say like, okay, this is what we are expecting from this application. Anything which is coming as positive or negative outside this, we can accept it as acceptable performance. Okay, so this is just a basic idea, or just this is a theory. In the next section, we are going to cover the memory management part. But before that, do you guys have, if you guys have any other question, just ask it via chat window. So I guess there is no question, so I will move to the other part. So this next section I'm going to discuss it over here, which is the main idea behind this meetup, is like this memory management or the IO management part is the memory management. So before I'm going to discuss about this memory management, what what do you guys think about this memory management, and why do we need this memory management or this memory at all? So any views, any ideas? Because I'm the only one who's talking, so you can reply it via chat window, or if not, I can proceed it further. I know it's Sunday, so we need to wrap it in 1 hour. Means I will try my best to wrap it in 1 hour. Okay, so if there is no response, I will move forward. So the kernel, which is the core of any of your operating system, has two major responsibilities. First, it need to interact with and control your hardware component, which is on the basis of the rings, like ring 0 to ring 3, which we are not going to discuss today. And the second one is to provide an environment in which your application can run. So to provide an environment in the sense like for any of the operating system or kernel, the most eliminatory part is to run up user space process. And for kernel to run the user space process, it needs to allocate some amount of memory. So kernel does that work really smartly to allocate the memory, because your load on your system is dynamic in nature. I mean, for example, right now the 10 process currently running in my system, but it might not be a situation after 1 hour. After 1 hour, it might be like a 20 process running in your system, or it might be a 5 process. So this load keeps on changing. So kernel need to handle this work really smartly to allocate a memory to a process or deallocate a memory to a process. Okay, so let's start with some of the demo part. So this is a command which I guess everybody run in your system in your daily day-to-day tasks, like free-m command. Okay, so this command will tell you like this is a total memory in your system, and this is a use byte, and this is a free byte. So this is like my virtual system in which I'm running CentOS. Okay, CentOS 6.6. So this is one of the most misleading factor, and why it is misleading we are going to discuss it right now. So before that, let's discuss about the different component. First one is the buffer memory. So what is exactly this buffer memory? So what exactly this buffer cache hold is like a disk blocks, and the reason it is holding this disk blocks to optimize your disk IO or a block IO. So I guess some of you are aware of the fact like a Dentries and inode. So every time I run this command ls or any operation which involve like a open system call or a stat system call, kernel needs a data which is present in your disk. So let's discuss this with the help of this demo. Okay, so in this terminal I will run this command. Okay, so it's going to refresh the screen for me after every 1 second, and here okay, so right now if you can see that currently the buffer memory is 14 MB and the cache memory is 75 MB. Let me run some command. I'm going to search it recursively inside your root directory. Okay, Kevin, I'm increasing the font size. Kevin, now are you able to see it? Is it fine now? I know it's difficult to see it on the smartphone or anything. Yeah, Kevin, somehow you need to manage it. So right now if you see that the buffer memory is 14 MB and the cache memory is 75 MB, let me run this command which is not going to do anything, just going to list your directory recursively inside your slash. So here if you can see your buffer memory got shoots up. So what kernel is doing right now is like to means it's going to hold all these entries which is called dentries or directories entries inside your buffer memories. So next time if the kernel need to do the same operation again, it is not going to go all the way to your disk to get those entries, but it will pick all those entries from your buffer. Okay, so while this operation is ending, you will see that the buffer memories keep on growing. Okay, and in the next demo we are going to see like how this cache is going to be increased or decreased. Okay, and if you guys need to check like how much is the entries or inode currently means occupied by these entries in your system, you can run this simple command proc/slab/info. I guess some of you are aware of this fact, like this is where your kernel data structure hold or the kernel objects hold. Proc/slab/info. Okay, and you can grab about this entries as well as inode. Okay, so in the upcoming session I'm going to discuss about each and every field, but this is just a basic. In this session I'm just going to give you a basic idea that this is the inode cache as a entry cache, and you need to focus on this active object as well as the object size. And means roughly the kernel is really a stable object, so you do not see many of the issues. But in case if you are seeing like your system is occupying too much amount of a memory, or a kernel is occupying too much amount of memory, you can check it over here, the slab, as well as you can check buffer here. Okay, so this is the first column, which is the buffer. Let's go to the other column, which is the cache. Okay, so like I told you earlier, the way the things work is like application, your application, and then you have a cache memory, and ultimately you have a disk. Okay, so first time when you are opening any application, let's say I am opening this file, cat abc. Okay, so this file is not present in your cache memory, or this is the first time you are creating this file. So what your application or what your kernel is doing is to going all the way to the disk, bringing that content into your cache, and then reading that, means populating your cache. So your disk, which is the slowest among all the components, for example, if you're comparing between your RAM, where your cache is holding, and the disk is like 1,000 times slower as compared to your RAM. Okay, so if the next time, if the same file need to be read, application doesn't need to go all the way to the disk to read this file. Application just pick this data to the cache. So means in the upcoming session, I'm going to talk something about like a perf, where you can see all this, and even you can look even up to the like a CPU level, like your L1 cache, L2 cache, or your L3 cache, which is present on your i7 system. Okay, so like in the last demo, we see about this how this buffer is populated. Same way we can see like how this cache memory is getting populated. So let me generate some IO. Okay, what this command is doing is going to copy entirely my hard disk partition dev SDA to a file called mnt test. Okay, so currently the buffer memory is 137 and the cache is 75. So what it is going to do, it's going to go inside each and every file. So it's going to populate my buffer, as well as the same time it's going to populate my cache memory. Okay, so you are seeing over here that buffer as well as the cache is getting populated over here. Okay, so just brief idea. Okay, so regarding buffer or cache memory, do you guys have any question, or I can proceed further? Okay, so I can proceed further. Before we are going to proceed further, there are some misconception about this cache memory. The first misconception is like, for example, I run this dd command. The moment this dd command exit, the people believe that the kernel will reclaim that memory as soon as this command exit. But this is not the case. So means kernel believes in the fact that the data which is read once is going to be read again. And at the same time, the kernel believes in the philosophy that any used RAM is a wasted resource. So like I run this command, kernel going to cache all this content, like I mentioned earlier, and the next time the application doesn't need to go all the way to a disk to read this content. The application going to read this content from your cache memory. Okay, so kernel believes in the idea that the data which is read once is going to be read again. So kernel doesn't going to discard your cache. It's going to keep all that data in a cache. The only case where the kernel going to discard this cache or going to flush the data which is present in the cache, in a case if you are facing some kind of a memory pressure. So let's say if you start any new application and that application requires some amount of memory, then in that case, kernel with the help of some of the flusher thread, which is like PD flush or per BDI flush, per BDI threads or kswapd, is going to flush all this data from your cache memory to the disk, and to make some room for this new application. But except for that, kernel is not going to discard your cache. It will keep that data in your cache forever if your system is not going to face any kind of a memory pressure. Okay, so this is one of the most important point which people like. This is a kind of a misleading, but I think I just want to share it with you guys. Okay, so means we are not going to discuss because this is just a basic session, so we are not going to discuss about all this LRU or least recently used algorithm, how kernel decide which data is going to discard or which data is going to keep, and active dirty pages. So like I mentioned in the earlier, like I'm going to start a new series where we are going to talk about this memory management or a process. Like I'm going to devote a whole day where we are going to discuss about all these things. Okay, so before we move further, I'm just going to tell you guys like there is one important package which I believe everyone should install in your test system for a quick reference, which is called kernel-doc. Okay, so this package has got wealth of information. So I believe like if anyone of you have wrote this Red Hat paper called Performance Tuning RH442, this is the first RPM which has been suggested by the Red Hat like to install in your system, because this RPM is really helpful not only on the paper point of view but in your day-to-day activities. Like this is a quick guide or quick reference whenever I am stuck at any place. This is the first place where I am look for any kind of a help. So here if you can see that this paper this folder has got the wealth of information, which is user shared doc, kernel doc documentation. Okay, so let's go back to our demo part where we are running this command called free-m. So here if you can see the buffer memory is 353 and cache memory is 88 and the free memory is 315 MB. And I guess most of you are using some kind of like a monitoring solution in your environment or in your company. And like for example, if in a case of a Nagios always reads this 315 as your free memory. But like I told you earlier, in case of a memory pressure, cache is the first place where the kernel looks to free up a memory. So your free memory is not exactly this. Your free memory is the sum of 315 plus 353 plus 88. So your currently the free memory present in your system is 757 MB. Okay, so this is your free memory. But still some people argue about it like, okay, no, our free memory is this much. So is there any way we can push this data or we can free up this buffer as well as cache memory? Okay, so here is some of the command which you can see. With the help of this, you can drop your caches as well as a buffer memory. I highly not recommending this command in your production environment, because kernel again need to spend some of the CPU cycle to build up your cache as well as a buffer. So for example, if you run this command, so currently the free memory is 313, buffer is 353 and 91 is my cache memory. Okay, so I'm running this command. So what it is going to do, it's going to drop my cache as well as my page cache, entries as well as inode. So again, if you're going to run free-m, you will see that your buffer is cleared as well as some of the cache memory is cleared, and right now you have 856 memory of free. So based on my experience, the only case where I recommended this command is like if your developer is doing some kind of a testing in your test environment and he find it out like his code is leaking some kind of a memory, or if there's a bug in their code and that data is being copied to your cache. So in that case, you can run this command to free up your cache, but except for that, this command is not recommended in any environment. You can use it in your test environment, but definitely not in your production environment. So if you just need to free up your entries as an inode, you can run this echo 2 and this. And if you just want to free up your page cache, you can run this command. And if you want to clear everything, you can run this command. Okay, so kernel-doc has got the wealth of information, and you just need to refer it to find out this command. Not only this, but it has got lot and lots of command. Okay, so only the swap part is left, which I'm going to discuss it after a few minutes. But before that, any questions so far? It seemed to be a really quiet session, so okay. Let's go to our day-to-day system administration activity. So one of the questions which has been asked by many people, like this is a command which I think everybody run on a day-to-day basis. And when I'm looking at the output of top, from the memory point of view, the 3 column of my interest is like this virtual memory, the resident memory, or the shared memory. As well as the same time, the proc by default sort out your process based on your CPU utilization. So the process which is going to do a much of a CPU utilization is in the top of the top list, as well as the other process following him. And if I'm going to run the shift with M, it's going to sort out the process based on my memory utilization. As well as if I press 1, it's going to break down based on my CPU 0 as well as the CPU 1. Okay, so this is just a basic idea. So let's go on to the memory part, which is a virtual memory. I think everybody is aware what is exactly the virtual memory, which is just a abstraction based on your architecture. Might be your 32-bit or your 64-bit. And I guess nobody is using 32-bit nowadays unless you are using some legacy stuff, because 32-bit always have an issue between your user space process as well as the kernel space process. So I think most of the infrastructure nowadays migrated to 64-bit. Res is your resident memory, which is your actual RAM. So whenever your process start, it will have like a big virtual address space, and then the memory mapping takes place between your virtual space and this RAM. And I think there's a device called MMU, which is called memory management unit, which is going to take care of this mapping. And then we have a shared memory. So is there a way to check the process which are consuming cache? Okay, so Anupam has asked one question: is there any way to check the process which are consuming cache? No, we can't. Because Anupam, these are not like actually I guess Google has developed one tool in which you can check like this file is present in a cache or not. I can give you that link after this presentation, but as far as I know, there is no way you can find it out like what are the processes which are currently present in your cache, because they are disk blocks. They are not actually the process. And I guess based on my experience, I always try to find out this answer of this question in your server fault or any other website. I even try to use some of the like a system tab script, but so far as I know, I don't know is there any way we can find out what are the processes which are currently present in the cache. So I think there are so many people, knowledgeable people who are present in this conference. So if anyone know how we can find out like this is a process which means what are the processes which are currently present in our cache, means as far as my knowledge are concerned, I don't know. We can find it out. Okay, so I'm going to share you the link, which I think is a Google project which they are trying to find it out. For example, you just need to run that script in one of your folder, and based on that output of the script, you will find out, okay, this file is present in cache or not. But if you need to find it out based on the output of free-m, okay, what are the content which are present inside the output of a cache? I don't think so there is any way right now which I know as far as my knowledge is concerned. Okay. So after this conference, I am going to share you that link. So yeah, let's back to the presentation. This resident memory, which is your actual memory. So one of the common question which has been asked by many people, Like when I'm going to sum up all the process present in my resident memory, which is the actual memory utilized by your process, it comes out greater than whatever the actual amount of RAM which is present in my system. So how that can be possible? Like how can the resident memory, like for example, this system has roughly around 1 GB of memory. And when I'm going to add up all these processes which is present in my resident memory, or how can the sum of all these processes will come out greater as compared as a sum of resident memory? So the answer to that question is something called a shared memory. So I guess everybody is aware of this proc, which is a kind of a virtual file system. And whatever the process which are currently running in your system, every process has its directory present over it, and inside that directory you have the data structure holding up that process present inside this directory. Okay. So for each and every process, we have two files. One is map, which is going to give you some basic information, and we have one file called smap, which is going to give you the elaborative amount of information, whatever the shared libraries, how much is the amount of memory this process is using. Okay. So every process is going to share memory with some other process or libraries with some other process. So here if you can see this process, I am inside proc1, which is the init process. Okay, so this process is having this shared clean as shared dirty this much. Okay, so this much 0 KB for this process, and this. And this process, this system is not doing much of a task, so this is expected. Or the other way we can find it out. Sorry. So here if you can look at this shared library, which is represented by read only, is being shared between different processes. So because of this shared concept, like this is a library which is being shared between different processes, you can see the output which is coming greater as compared to your existing RAM. So if you need to find it out, like how much is the actual memory which is being utilized by my system, you can go inside this proc smap and minus all the shared memory, and in this way you can find it out like how much is the actual memory which is being utilized by your system. Or if you don't want to do that, I have one script which I copied from this GitHub, and with the help of this script you can find it out like how much is the actual memory which is being utilized by my system. I'm just sharing it with you guys. So this is mainly a Python script, and it is wrote by one of the open source enthusiasts. So to run this script, you need to have a Python installed in your system. Okay. So this is going to tell you how much is the actual memory which is being used by your system minus the shared memory. Here if you can see, like it will going to tell you what is the private memory which is held by this process and how much is the shared bit. Okay. Before you are going to ask anything, let me tell you one thing about this script is like a catch regarding the script. For example, this Apache process. So I think everybody is aware like Apache start first process a root to bind to any of the port between 0 to 1024, and after that it will fork all the child process. So what the script will do, it will not going to give you the output or the memory occupied by each and individual process. It's just going to give you the cumulative sum of all the process. So this is one of the catch with this script. Except for that, this script runs really good, and it will give you the clear idea about your system, like how much is the actual memory which is being utilized by your system. For example, it is showing as like here 148, but this also involved like some kind of a share or all those pages. So just try to install Python and run the script to find it out how much is the actual memory which is being utilized by your system. Okay. So any questions so far regarding the script or virtual or shared or resident memory? Okay. So if not, let's move to the other slide. Okay. So far we have covered buffer, your cache, your drop cache, and last part which is left is the swap memory. Okay. So I think like I started my Reddit journey is almost like or Linux journey almost 10 years back, where we don't have like a abundance amount of memory. For example, we don't have like a GBs or terabytes of memory which is present nowadays. So at that time, I think most of the vendors like Red Hat or any other vendors which is present at that time, they recommend like the amount of swap which is currently present in your system is almost like a 2 times of your memories or at least 1.5 times. But nowadays that situation doesn't left. Most of our system is like having at least of GBs of memories or terabytes of memory which is present in your system. So if we look at the swap part, swap is basically we can say that it's the extension of your memory area. So when your kernel decided not to get memory from any other resources, it starts swapping. Okay, so it's just a safe measure which has been used by a kernel nowadays. So like one of the basic question which has been asked by many people, like my system has got a plenty of RAM, but still my system is swapping. Is this is good or this is normal, or why this is happening? Means my system has got enough amount of memory, but still my system is swapping. How can this be possible? And the simple answer to that query is yes, your system can even swap even if you have a plenty of amount of memory present in your system. And the reason for that is like, for example, whenever your system starts or whenever your OS boots up, the first process which starts is the init process. Okay, it do some incredible amount of stuff. For example, you're setting your system at startup as well as the reshapening your login attempt if they are dying. But do you guys think like once your system boots up, do we really need that data? Or kernel can make room for some more important data which is currently running in your system so that in case of any kind of a memory pressure or in case if that data is needed from the cache, the kernel or the application don't need to go all the way to the disk to get that data. So your system can even swap if you have a plenty of amount of RAM still left. Okay. The only case where you can see a real amount of a performance issue, or we can say it's a swap thrashing, uh, when you run this command vmstat and you constantly see that your system is doing swap in as well as a swap out. That means your system is facing some kind of a memory issue. Okay. Except for that, if you find some of the data which is present in your swap, that is perfectly okay. But if your system is constantly writing the data inside the swap, then there might be some kind of a memory or a performance issue. Okay. And like I mentioned earlier, in case of a cache, whenever your process exit, kernel doesn't try to reclaim that memory because it will believe in the fact that that data can be read in the future by some other process. The same theory applied for swap memory also. So if some process swapped in a case of a memory pressure, kernel doesn't try to reclaim that data from your swap memory once that pressure is resolved. So that data will lie in your swap memories forever if you are not going to face any kind of a memory issue. And I read some of the forums where they have mentioned like you can run the swap off operation and swap on to clear at that swap space. Let me tell you, please don't run swap off or swap on to flush out that memory, because swap off is really an expensive operation. It's really slow. And what it will does, for example, let's say my system has a 500 MB of memory, and let's say just in for the case of discussion, this all this 500 MB of memory is occupied by a swap. So whenever you do a swap off, first thing it will do, it will check if your system has 500 MB of memory left. And if your system doesn't have that much amount of swap free memory available at that particular moment of time, it's just going to kill your system. It's just going to make your system really, really slow. And ultimately that operation will fail. Okay. So the second thing I'm going to show you guys, like, is there any way are you guys able to hear me? Because I'm getting some Yeah, Anupam, I'm going to discuss it means during the tuning section, like what are the parameters we are going to use. So just wait for 5 more minutes. I'm going to discuss about this swapness parameter. Yeah, that is really important. Okay, so the first question which is going to be asked by many people, like if that swap memory is occupied, how can we find it out? What are the process which lies inside this swap? So is there any way we can find it out? So there is a one simple script with the help of which you guys can find it out. What are the process which are lies inside this swap memory? Okay. So like Anupam asked earlier, is there any way we can find out what are the process which is lies inside your cache? That is not possible, but you can find out what are the process which are swapping. But at the same time, this is applied for only the process which are actively swapping. If there are process which is swapped earlier and that process doesn't no longer exist, we cannot find it out. Okay, so I have this script memory check 2000M. This is just my custom script, so I'm going to generate some of the memory. I'm just going to map some of the memory. So here you can see that this system starts swapping, and right now it's like having a 54 MB of swapped space used. So the script I've shared with you guys, with the help of this script you can find out what are the process which is currently swapping right now. Okay, so just run this script, and it's just a simple shell script, and it's the same way it's going inside your smap folder or smap file, and look for this parameter. So I guess you can write your own custom script with the help of you, which you can go inside each and every folder, or you can use this script to find out what are the process which are swapping. Okay. So this is some of the tunables which we can use to improve the performance of a system. Like these are some of the recommendation, like the one which I pasted from one of the Reddit forums. This is some of the recommendation which Reddit suggested for while setting up your Oracle system or Oracle database. Okay, so before we are going to discuss this, okay, these are some of the default parameters and for swappiness which Anupam asked earlier. Okay, so before we are going to discuss about all these parameters, let me go back to my ASCII art again. Okay, so I guess any of the application, mostly like for example Oracle, which are not going to do the direct IO operation, that is not going to write directly to a disk. All the application first write its data inside the cache, and then with the help of some of the kernel thread, which might be your PD flush or per BDI flush thread, it's going to push the data inside your disk. So in case of a RHEL 6 or CentOS 6, you find out something called a per BDI. Okay, so okay, sorry, this BDI threads. Okay, so application first writes its data from inside the cache, because I think most of you are aware that the kernel uses something called a write back cache. So it's not going to flush data immediately into your disk. First it writes all the dirty data into your cache, and in cache that data has been there for some period of time, and then we have a number of threads which is running on the background, which is going to push that data back to the disk, and these are the threads. BDI default, or guess in case if you are using a CentOS 5 or a RHEL 5, you will find PD flush thread. Okay, so these parameters, this dirty background, all these parameters will refer to those threads. So for example, if my VM dirty ratio is like 20, that means this is a percentage of total memory in which the number of pages at which the process which is generating a disk write is going to itself start writing the data back to the disk. Okay, and in the same way, the background ratio refers to the this flusher threads, BDI-default. That is means the percentage of total memory at which the number of pages at which the background kernel flusher thread will start writing out the dirty data. So for example, if you set this to 10, so 10% of the total system memory that include your this RAM, whenever your memory is dirtied up to that much amount, these threads will automatically start writing your data back to the disk. Okay, and the same applied for this centisecond and all these threads. So if you guys want more information about these threads or any of these parameters, like I told you, the best place to look is, this is where I mostly look for any of them. Okay. And regarding your question, Anupam, means I'm not going to discuss more about this, but this is the algorithm which kernel used. Okay, so first go to these parameters. So here you can find all the information about these parameters, like how we can tune these parameters. So generally, if you look at the Red Hat documentation, mostly following the Red Hat. So they said that most of the system they come out default installed with the Red Hat, they are mostly tuned and they mostly going to work with 90% of the infrastructure. But if you want to get a more improved performance from your application, you need to tune your system. So let's say these threads will work fine in 90% of the environment, but if your application is doing so many amount of write that is going to dirty your pages at a much frequent interval as compared to the normal application, then in that case you need to tune these parameters. So for example, the value of the background ratio or this dirty background ratio is 10 by default, let's say, but because your application like Oracle is doing so many amount of small writes, or it's going to dirty lot of amount of small pages. So in that case, you need to lower down this value to 3. But it's all depend based on your application to application. For generalized environment, it works fine. But if you are using some special kind of application, yeah, in that case, you need to tune your system. Okay. So these are just some of the general guidelines which is provided by Red Hat if you are going to use Oracle or Oracle RAG cluster in your environment. Okay, and the more information about it, you can find it over here in the memory management section, which I am going to discuss in the upcoming meetup. I'm going to discuss about all these parameters, but this is just a general idea about all these parameters. Okay. So this is all about memory part. If you guys have any question about the memory, please stop me or please ask it via the chat window. If not, we have 10 minutes left. So let's start this IO subsystem. Okay. So this is just a generalized diagram which I copied from the IBM this red books. So this is how any user process or any application ultimately write the data to a disk. So let's say in this case we have some data which has already been copied from your disk and currently present in your page cache. which we have discussed it so far. Then we have this PD flush thread or BDI default thread in case of a rel 6, which is going to flush the data from this your page cache ultimately to this scheduler layer. So what exactly happens in that scheduler layer is that the merging of your requests will take place, and how this merging will take place will depend upon the type of a scheduler you are going to use. So we are going to discuss about scheduler in like next 1 or 2 minutes. Then you have a device driver. One of the common misconceptions about device driver, that device driver is going to queue your request. No, device driver, what device driver will do is just going to repackage your request and going to be present it to your disk to the format which has been understood by your disk. So it's just going to do the repackaging of this your data and just going to write it into your disk or hand it over to your firmware. So the first tool which I am going to discuss is today is called IOStat. So if you run IOStat without any other option, it's just going to give you the output which is which is not helpful for in many cases to debug any of your IO issue. So I guess most of you are aware of that the IOStat read this file called disstat, and it's going to present you the data which has been like more friendly in nature, human friendly in nature. Okay. Now let's run IOStat with some other option, TKX-P1 and 3. Now you will see some of the data which is like more helpful for you and mostly helpful for you in debugging any of the IO related issue. So always discard this first column because this is the data which is being read when your system boots up. So this is not very much helpful. We need to focus starting from this area. Okay. So let's run IO with, let's say, 1000. Okay. And let's generate some IO. Okay, let's do the same stuff again. And I'm writing some test file with a block size of 1K and count equal to, let's say, any number of count. Okay. So here if you can see that it starts generating some IO. Okay. Your read request, your merging, everything is increasing. Just remove this file. Okay. So here I am not going to discuss about each and every parameter. I'm just going to discuss what are the parameters which is really helpful for us in case of debugging any IO related issue. Sorry. So the first thing is RRQM, which is the read request merge per second, and second one is the write request merge per second. Okay. So if we go back to the previous diagram, this is where your request merging is taking place. Where is the scheduler? Okay. So this one, scheduler. CFQ is a general purpose scheduler which has been used, and it's a default scheduler in case of your Red Hat 6 operating system. Or I think starting from Red Hat 5.2 or 5.4, CFQ is a default scheduler. Before that, Deadline is a default scheduler, but now Deadline or Anticipatory, I'm not sure. But nowadays CFQ is a default scheduler, and in case of RHEL 7 or CentOS 7, they have put Deadline for some disk and CFQ for others. And Anticipatory no longer exists in case of a RHEL 7. Okay. So whenever your requests reach from your page cache up to the scheduler layer, the merging of requests will take place. So what do you mean by the term merging? So you have a different sets of disk blocks here, here, here. So instead, like it is going to send out a request for this different layer or different blocks. It's going to merge the request so that your head doesn't need to move a lot. So what this will helpful that is going to reduce your seek time. So let's say if you have a file A1, A2, A3, and which has been dispersed at different places. So what scheduler layer will do, it is going to merge all this so that at a once this file we will write to this place at A. It doesn't need to scatter around all over the disk. Okay, so this is what scheduler will do. It's going to merge your request. It's going to do a lot of other stuff. For example, if you are using a deadline, it's going to prioritize read over the write request. But whatever the scheduler you are going to use, it depends upon your environment and whatever the type of application you are using. So let's say if I'm using a database, then in that case, deadline is the one which is recommended. If you are using some kind of a virtual environment, for example, VMware or KVM, then case Noop or no operation is recommended. Okay, it's depend upon your requirement, whatever the what type of scheduler you are going to use, and this will directly impact your TKX-P. This merging of requests, read request merge per second as well as the write request merge per second. And between, I forget to told you, like this is T represent for time, K for kilobyte, X is for getting this extended output, and P is for per partition base. So I guess if you guys run this command in case of a RHEL 5 or CentOS 5, this X and P are mutually exclusive. But in case of RHEL 6, because I am running something called CentOS 6.6, so here if you need to get this per partition breakout, you need to specify this -p parameter. Okay, so this is one thing. Now let's look at some important parameter, like this is the number of requests which is read, write, number of data transfer. Now the second most important parameter is the average queue size. Okay, and what is exactly this queue size and how this impact this your percentage utilization. So let's go back to this, or I can draw some simple art. So this is your IO scheduler, ultimately your driver, and ultimately the data will return to the disk. At IO scheduler layer, you have something called a queue maintained called NR request, and here at storage level or a disk level, you have some queue called queue depth. Okay, so as long as this request queue is below this queue depth, your IO will flow smoothly from scheduler layer to a disk layer. Okay, so here the number of requests which has been maintained over here, if below this point, this level, your IO will flow smoothly from scheduler to driver to your disk. The issues start arising when this number of requests, when this queue start building up. So let's say if I'm using like a really high end system and I'm using some 7200 RPM disk, so my disk is not smart enough to fulfill my request. So here this scheduler layer goes to be built up and my device queue is small. So it is not going to process your request as fast as my system is requiring. And there, in that case, you will see this percentage utilization, the last column. Sorry, this percentage column goes increasing. Okay, so let me explain it one more time. This NR request must be below this queue depth. If this request start building up and this your disk is not able to fulfill your request, then in that case your utilization column got shoot up, or you will start average wait. Like your application start waiting, and most of guys are aware of the D state process or uninterruptible sleep process, where D state process goes to be increased or start building, and you will see the load average, which is this much, start increasing in your system. Okay, I guess, yeah, most of you guys are aware of this concept. If you have any question right now, just ask me. And the way you can see this number of requests is this block depending upon your disk and queue nr underscore request. And same way you can see your disk queue depth is inside device queue depth. Okay, and like I told you earlier, your driver is not going to queue any request. Okay, Now the second question is, if this NR request start a building, how can I tune this parameter? So let me tell you, like there is no best setting you can do for this NR underscore request. Whatever the optimum value you are going to choose will depend upon your underlying file system and your IO workload characteristic. So before setting up this parameter, this 128, this is the by default which comes out. You need to set up some kind of a benchmark in your test environment. Like what is the parameter which is best suited according to your environment. Okay. So based on my experience, if my IO size is smaller, I choose this value to be high. Means in that case, it shows me some better result. But that will depend upon my application, whatever I tested in my test environment, or in my PLT environment, or in my testing environment, or in the developer environment. But it might be different for your application. So before putting up this parameter, just check it thoroughly. Okay, I think we already exceed the time, so I'm just going to take 5 more minutes of you guys, and after that we will wind it up. So when this IO stat, when I first use this IO stat, the basic issue which I have faced is like, okay, yeah, I find it out like, okay, this is the issue which I am facing and it is related to IO, but somehow I am not able to find it out, okay, which process is causing this IO, or which process is responsible for causing this IO. So if you are using a RHEL 5.8, from there onwards they introduce something called IO top. Okay, which also give you what are the process which is responsible for generating IO for us. So here if you can see the disk read, disk write, and the last column even show you what are the process which is generating IO for us. So let's run our DD again. Okay, let's do it this way. Okay, right now it's not doing any IO. Let's generate some data. Okay, so here you can see that DD is the command which is generating IO for us, and then we have a flusher thread which is going to push the data back to our disk. Okay. So IO top, the good thing about the IO top, here you can clearly see which is the process which is generating IO for us. Okay, but IO top has one limitation. First, for IO top to work, you have something called proc self or IO. This file need to be exist, and this file is only present after Red Hat 5.8, and you need to have your kernel configured with one of the parameter called config underscore task underscore IO underscore accounting, this much. This parameter need to be compiled inside your kernel. So in case if I am running any system which is below Red Hat 5.8, what should I need to do? If I need to find it out, which is the process which is creating IO or which is creating bottleneck in my system, how can I find it out? So in that case, I guess some of you guys are aware of the something called system tab, which is like a tracing mechanism, and it has been there for a while. In case of a Solaris, we have something called dtrace. So there are many people like Brendan Gregg who converted most of your dtrace script to a system tab script. And I never use dtrace in Linux environment because nowadays it's available, but I mostly rely on system tab to debug some complex performance issue. So if you are running your any system before RHEL 5.8, you can use this user share. Okay, so it will give you almost like a similar output like IO top to find it out like which is the process which is going to generate IO for us. So this is some advanced tool, system tab. In one of the upcoming session, I'm going to discuss about the system tab, perf, and BLK trace, which I'm using heavily to debug any of this CPU IO or a memory issue. But this is just for the demonstration purpose. So like it will give you which is the process which is generating IO for us, read and write. Okay. So I think we have covered everything. So this is just a brief introduction about the IO and memory. I know we just scratched the surface and we just covered some of the basic parameters as well as some basic command. But I will promise you that I am going to come up with something like more elaborative in the upcoming session. And we have some really knowledgeable people in this call. So I am really thankful to you guys, like you spare some of your Sunday time and come in this conference. And with the upcoming meetup details, we are going to post it soon. So in case you guys have any question, I'm still here for 10 more minutes. So if you guys have any question, you can ask me via this chat window. But I really appreciate it, and thanks once again. Just one last thing, I am going to update this presentation means in a YouTube after an hour or at the end of the today, and I'm going to send you a link to all you people.